All right, Chem 1110 students, we're going to cover Chapter 10 in this one video. It's a fairly short chapter talking about the energy changes involved in chemical reactions. When we look at those energy changes, we consider the system to be the chemical reaction and everything else to be the surroundings. And so what we are looking at is the um, energy changes for the reaction itself and how it affects the surroundings with this kind of diagram. So this study of the energy or heat energy changes for a chemical reaction is called thermochemistry, and heat is a term used for that transfer of thermal energy. So it is going to be absorbed or released from virtually every chemical reaction, and so we have a unit for that, and that unit is called the joule. Now in this country, we most typically use the unit of calorie. That's the one we are familiar with. But we have to look at that equivalency between the calorie and the joule. And so 1 calorie is 4.184 joules. This is not the nutritional calorie. A nutritional calorie is 1,000 of these calorie units, which is the amount of heat required to raise 1 gram of water 1 degree C. So what we need to look at is some reactions are exothermic. These produce heat and it transfers it to the surroundings. And if you are in those surroundings, you would say it feels hot. Here is a really dramatic example. The Hindenburg blimp was filled with hydrogen. That's why it floated, because hydrogen is lighter than air. But when it got to an ignition source, it hit a radio tower. It caused it to react with the oxygen in the air, and lots of energy was released. And so in this case, it not only felt hot, you could see the light and everything else. A lot of energy there. If energy is absorbed by a chemical system, then the heat energy moves from the surroundings to that chemical system, so the surroundings feel cold. And an example of this is the melting of ice cubes, solid water to produce liquid water. If you have solid ice cubes in a glass, at room temperature, the heat from the surroundings will move into the ice and cause it to melt, and the glass will feel cold to you. So in this case, our blue arrow is moving from the surroundings to the system. We actually measure this heat change using a calorimeter, or that study is called calorimetry. And so the device is a calorimeter, and we have some other quantities we talk about. There is specific heat, which is that amount of heat required to raise 1 gram of a substance by 1 degree C. This has been tabulated for a lot of things. And we've also talked about heat capacity, and this is the amount of heat to raise the temperature of an object by 1 degree C. So we've removed the mass from this, and an example here would be the heat capacity of 1,000 grams of water. You would take that specific heat and multiply it by 1,000. The way it's done for most substances is to ratio the specific heat of the material, say aluminum, to the specific heat of water, which in calories is just dividing by 1. So the units for specific heat is joules per gram degree C, whereas heat capacity, we've removed that mass. And here is a very important set of equations where Q is allowed to stand for heat. So if you're using the specific heat, you have to multiply it by the mass and the change in temperature. If you're using heat capacity, you just multiply the heat capacity by the change in temperature to get that heat. Note that for the change in temperature, we take the final minus the initial. So if your temperature is dropping, that's actually a negative number. So here's an example that I will do in class about, how you would use those equations to calculate heat involved. Here's a second example. And now we're going to talk about how it's actually measured in the lab, which is generally going to be constant pressure because you're just doing it in a lab. You're not changing the pressure, which is pretty well defined by where you are above sea level. And in next week's lab, you'll be using a coffee cup calorimeter. And so the basis of a coffee cup calorimeter is that you have the reactants sitting maybe in a vessel inside that inner coffee cup, and there's water around it. And so what you're looking at is the change in temperature of that water. This first reaction listed for some of these typical heats measured at constant pressure, the neutralization of HCl and NaOH would be pretty simple to do in a coffee cup calorimeter. The other ones would be a bit more difficult, but it's examples of ones that have been measured over time. So if you're looking at this constant pressure calorimeter, there's certain things you need to understand. So the heat has a sub P, meaning its constant pressure is equal to the enthalpy. So the enthalpy of a reaction is always measured at a constant pressure. And what that's saying is the system is a chemical reaction and the surroundings are the water in the calorimeter. So for an exothermic reaction, the chemical system is losing the heat and the water is going to be absorbing the heat. And so here's the equations. The heat for the system, meaning the chemical reaction, is going to be lost, and that's we have a negative sign, so we have the mass times the specific heat times the change in temperature. The surroundings is gaining it, so it's positive. So here we see that the heat for the system is opposite in sign to the heat change for the surroundings. And we have an example here that I will do in class about a calorimetry kind of experiment. The other topic we are going to discuss is Hess's law. And basically what Hess's law says, if you want to know the heat or the enthalpy changed for a reaction and you can't run that reaction, but you have other ones you can add up to get that one. So, a stepwise process that would produce the reaction you want, you can actually just add up those enthalpies. And so an example here is a combustion of methane producing liquid water, but the production or the combustion of methane is like what happens on a natural gas stove. It's very hot, so no water is going to be in the liquid form. It's going to be vapor. So what they're showing you here is you can take that delta H for the first reaction, combine it with the change in enthalpy for vaporizing liquid water, and you would get the overall reaction for the combustion of methane to produce water vapor. And here's a little diagram of it. So you have a heat energy for your reactants, that's methane plus the oxygen. When it burns, it releases a lot of energy, which is why we do that reaction. That energy comes from the changes in the chemical bonds, how the chemical bonds are broken. But then we're recognizing we have to use a little bit of that heat to vaporize water, so we have a short arrow that goes up to the right, and the net effect is that fat arrow all the way to the right. So there are some things you need to remember when applying Hess's law. You can manipulate other equations however you need to get the desired equation, but when doing those manipulations, there's some rules. You have to use your physical states. So for instance, you recognize your liquid water has to go to vapor phase water. If you have to multiply a reaction by a factor, you've got to multiply the delta H, and we're going to do an example in a minute where you'll see this. If you have to reverse a reaction, if you have to turn it around, you can do that. You just have to change the sign on the delta H. Then you add up all the delta H's for each step, and you have found the overall reaction enthalpy. And we generally use this when we can't actually run the reaction. So an example I have here for you is we have this target reaction of NO gas reacting with monatomic oxygen to produce NO2. Not a reaction we can do in the lab, but we could do these other ones, reaction of NO with ozone to produce NO2. We can take ozone and break it down into oxygen, or we can take oxygen and diatomic oxygen and break it down into monatomic. So we're going to take those reactions and their associated enthalpies to get our target reaction. Start out by writing our target reaction up here so we can see where we're going, and we'll use that first reaction listed on the previous slide because it has NO as a reactant, which we want. And then in the second reaction, we want to use the second reaction to get rid of the ozone. And so we have to turn it around. That's what they mean by reversing it. So the ozone, the O3, is a product. So we change the sign on that delta H. And when we add those up, we now have NO plus half an O2 gives us our NO2 with an associated minus 56.6 kilojoules per mole. And then to get rid of that half of a diatomic in order to get monatomic, we use the last equation that was listed, but we divide it by 2 and reverse its direction. And so when we add that with the other step that we had on the other page, we get our overall reaction. We see the delta H is minus 304 kilojoules per mole. Okay, the other topic we're going to talk about is standard enthalpies of formation, and this is very useful. It sort of gives us a baseline because what it says is a delta H of formation of any compound is the energy it would take to make it from its constituent elements. And so, for instance, if you want to make CO2, you make it from solid carbon and oxygen gas. And the important thing is a third thing here, that the delta H of formation for any element in its stable form, so how it exists in nature, is 0. And these are actually tabulated in your textbook and many other reference books. So you can use those standard enthalpies of formation to come up with a standard enthalpy for a reaction. And so your reaction could be A plus B gives you C plus D with those stoichiometric coefficients. And so basically what this says is you can take the products and subtract the standard enthalpies of formation for the products and subtract the reactants. And I've just written it differently with some signs here, the capital sigma. And the N and the M are your stoichiometric coefficients. And so here is an example we will work through in so we have graphite plus O2 producing CO2 because we're wanting the formation of C2H2. So we have these standard reaction enthalpies, and we will do that in the Zoom.